Dipole intermolecular force comes about because of the fact that some bonds inside of molecules have a bond dipole moment. So to understand this, we need to look at the idea of electronegativity. Electronegativity was a periodic trend that we talked about, and this is a measure of an atom's ability to pull on electrons inside of a bond. Remember that the periodic trend was that electronegativity tends to increase as we go up and to the right on the periodic table. The way I like to remember this is that fluorine is the most electronegative element. And if we have a covalent bond where the two atoms inside of that bond don't have the same electronegativity, by that we mean usually that they're not the same molecule, what we do is create a polar covalent bond. And this is because the electron pair inside of that bond is not equally shared. So if I have a bond here between atom A and atom B, and if atom A is more electronegative than atom B, the electrons inside this bond are shifted slightly closer to atom E and they're pulled away from atom B. Overall, what this does is it gives atom A a slight negative charge. This gives atom B a slight positive charge. So when we look at a molecule, what we do is we look at the vector sum of all of these bond dipole moments. So vectors are kind of a scary math term, but really we're saying are these polar bonds pulling in a certain direction, or are they canceling each other out? Depending on this, the overall molecule can have a dipole moment or have a dipole. And remember, when we say dipole, we mean that there is a shift of electrons and that the molecule has a defined positive and a defined negative side. So here, if I look at this, if I have two bonds with a dipole moment, and if these two bonds are kind of pointing in the same direction, yeah, one side of this molecule is going to have more electrons and the other side is going to have less electrons. So this molecule would have a dipole and therefore a dipole intermolecular force. And so we'll see, you actually have to look at some real examples to understand this a little bit better. But it is possible for my bonds to be equally canceling each other out. So I like to talk about this as like a tug of war. If you have two things pulling on opposite sides, you really don't get a separation of the two. So if I have two bonds here in my theoretical molecule, one's pulling one way, the other one's pulling in the exact opposite direction, those dipole vectors from the bonds cancel each other out. And overall, this molecule would not have a dipole, and the molecule would be considered nonpolar. So we need to understand, what situations are like this, where the bond dipole moments are pushing in a specific direction, giving my molecule a dipole, or when are they canceling each other out. So what we can say is that when we do have a polar molecule, polar molecules tend to have a stronger intermolecular force than nonpolar molecules. And this is because of this charge separation that we're talking about. So each molecule inside of my substance has a slight negative and a slight positive charge. So the positive charge from one side of the molecule can interact with the slight negative charge on a different molecule. This causes an intermolecular force between these two called the dipole intermolecular force. So overall, the question is the molecule polar? If it's polar, then the molecule has a dipole. It has a dipole intermolecular force, and we know it has a stronger intermolecular force than, say, things that are nonpolar. So how do I determine if something is polar or nonpolar? And this is kind of a tricky question, and really what we're saying is, do the bonds point in a specific direction, or do they kind of cancel each other out? And this is something, it takes you quite a while as a chemist to be able to look at something and truly be able to tell if it's polar or nonpolar. But what I want to give you now is kind of like a base set to get you guys thinking about it. And what it all has to do with is the geometry of my central molecule. So my central atom in my molecule. So there's going to be more complex molecules. So this idea of is a molecule polar or not is kind of a complex question. In this case, we're just going to be looking at a molecule with a single central atom and with some things attached around it. The question I want to ask is what's the molecular geometry of my central atom? And remember, when we look at this, we're not looking at the lone pair electrons, so it's not the electron group geometry. We're asking for the molecular geometry of what my central atom is. And just to remind you guys of this, so we kind of went over this when we were talking about VSEPR and shapes. how we figure out the geometry is by counting the number of electron groups that are around the central atom. And so remember, the electron group can either be a set of lone pair electrons or a single, double, or triple bond. And this is one of the major mistakes people make. I don't care if there's one line, a single bond, two lines, a double bond, or three lines, a triple bond. I don't care if there's 6 electrons inside of that bond. It's still counted as one electron group. With this, the geometry also depends on, are those electron groups a bond or are they lone pair electrons? So this is kind of a review, but if I have 2 bonds around my central atom, the molecular geometry is linear. 3 bonds, it's trigonal planar. If I have 2 bonds and 1 set of lone pair electrons, it's bent. 1 bond, 2 sets of lone pair electrons, it's linear. 4 sets of electrons, if they're all bonds, tetrahedral. 3 bonds, 1 set of lone pair electrons, trigonal pyramidal. 2 bonds and 2 sets of lone pair electrons, it's bent. 1 bond and 3 lone pair electrons, it's linear. And so there are, the 5 and 6 sets of electrons. We really don't see these, especially inside of organic chemistry. And it's better just to look at this small set. So we're really only going to look at a central atom that has up to 4 sets of electrons allowed it. And once you understand that, you can kind of extrapolate and understand other situations. So the way I like to look at it is I consider the fact that most molecules are polar. So if you just grab a random molecule out of thin air, most likely that molecule is going to be polar. And the reason why is it takes a very specific set of circumstances to make a molecule nonpolar. So all the bond vectors need to cancel each other out, and that's actually kind of hard to do. So it's easier to ask yourself, is a molecule nonpolar? And then you say, does it have those specific set of circumstances to make it nonpolar? And if the answer is no, well, then your molecule's polar. So if you look at it, there's only some very set circumstances that can allow a molecule to be nonpolar. So with this, molecules or central atoms with the molecular geometry of trigonal planar and tetrahedral can only be nonpolar if all the substituents, by that the things that are attached to my central atom, are all the same. That's the only way that those 2 geometries can be nonpolar. So if I have 2 different types of substituents, it's polar. Same thing with the molecular geometry of linear. The only way a linear molecule can be nonpolar is if the molecule is symmetrical. By that I mean it has the same things on opposite sides. So symmetry is a really important idea in chemistry. We need to be able to say, can we draw a line down the middle and do I have the same thing on the left as I do on the right? And that's really what we're talking about when we're saying the bond vectors are canceling each other out. There needs to be one thing on one side, one thing on another, pulling against each other equally. And that happens in a linear molecule only when the molecule's symmetrical. So once again, that's something that we want to look at. And these are the only set circumstances where a molecule can be nonpolar. Any other situation, any other molecular geometry, the molecule is polar. So this is one where you really need to look at some examples to understand what's going on. And really the question is the following molecules polar or nonpolar? And we're asking, does the molecule have a dipole intermolecular force or not? And in a little while we're going to combine all these together and figure out what's the strongest intermolecular force in something. But for right now, this is one of your skills, is to be able to look at a molecule and say, is the molecule polar? And by polar I mean there's going to be a separation of the electrons surrounding that molecule such that there's a slight negative charge on one side and a slight positive charge on the other side. So when we look at this first molecule, molecule 1, you can see that it's linear. So my central atoms have 2 groups of electrons, so a single bond and a triple bond count as a group of electrons. So this is symmetrical. And we know this because I can draw a line down the middle such that I have the same thing on one side as I do on the other. So it's like a tug of war. I have a carbon and a fluorine on one side pulling in one direction. I have a carbon and a fluorine on the other side pulling in the other direction. They're canceling each other out. Because they're doing that, overall, this molecule is going to be nonpolar. So don't get me wrong, these CF bonds do have a bond dipole moment, but they are canceling each other out. So overall, this molecule is nonpolar. So it's linear and it's symmetrical, so it's nonpolar. When we look at molecule Q over here, we see that it is not symmetrical. So it's still a linear geometry, but when I try to draw a line down the middle, I don't have the same thing on the left as I do on the right. And really what it's going to come down to is a chlorine pulling on one side and a fluorine pulling on the other. And really what's going to happen, remember fluorine's the most electronegative element, so the electrons inside of this molecule are going to be pulled more on this side. So this side of the molecule is going to have a slight negative charge, this side is going to have a slight positive charge. The molecule is going to be polar, it's going to have a dipole intermolecular force. So it's linear and it's not symmetrical, so it is polar. So we go to 3 here, and the first thing I want to look at is what's the molecular geometry of the central atom inside of here. So there's 1, 2, 3, 4 groups of electrons, but one of those groups of electrons is a lone pair electron. So this is trigonal pyramidal. There's no way I can make a molecule where the central atom is trigonal pyramidal nonpolar. So I'm always going to have a set of lone pair electrons on one side. That's always going to cause a separation of charge. So it's not on my list of the possibilities that can make a molecule nonpolar. So I know because the central atom is trigonal pyramidal, this molecule is polar. I don't need to consider anything more about it. So with molecule 4, same thing. I look at the central atom, 1, 2, 3, 4 groups of electrons inside of there. They're all bonds, so this molecule is tetrahedral. And the rule is the only way I can make a tetrahedral molecule nonpolar is if the substituents are all the same. So here, everything attached to my central atom is a hydrogen, and it's a little hard to see if you actually grab a tetrahedral molecule. Overall, all these bonds are canceling each other out. It's a little hard to see in 2D here, and that's why I use the rule. The only way I can make a tetrahedral molecule nonpolar is for all of the substituents to be the same. So all of these bond dipole moments are canceling each other out. So 4 is tetrahedral molecular geometry. With all the substituents the same, it's nonpolar. So 5 is a little bit different. It's still tetrahedral. Got my carbon, 4 bonds. It's tetrahedral, but all the substituents are not the same. So I have 2 hydrogens and 2 chlorines. And this is where it gets tricky. You can kind of look at this, and sometimes when people draw tetrahedral molecules, they'll put these bonds at 180 degrees. You got to remember the bond angle inside of a tetrahedral molecule is 109.5. So really these chlorines are pointing in one direction, these hydrogens are pointing in the other direction. Don't be fooled by the way people draw 3D molecules. This chlorine and this chlorine are not canceling each other out. They're actually pointing in the same direction. That's why I use the rule. The only way I can make a tetrahedral molecule nonpolar is if all the substituents are the same. Like here. Here I have 2 different sets of substituents. The molecule's polar.